When we think of lightning, we picture brilliant flashes illuminating storm clouds. But there's another type of lightning occurring alongside these storms that we can't see at all. It's called dark lightning, a mysterious phenomenon that shoots beams of antimatter and gamma radiation upward from thunderclouds toward space. First detected in 1994 but only seriously studied in the last decade, these terrestrial gamma-ray flashes represent one of the most energetic natural phenomena in Earth's atmosphere. Today, we'll explore this invisible force, how it affects aviation safety, and why scientists are racing to understand it better. Dark lightning was first detected in 1994, but it wasn't until the past decade that scientists began to seriously study this phenomenon. Unlike conventional lightning that creates visible plasma channels, dark lightning releases energy through gamma rays that are completely invisible to the human eye. According to recent studies published in 2023 by researchers at the University of California, these events occur approximately 1,000 times daily across our planet. They're most prevalent along the equatorial belt where thunderstorm activity reaches its peak. This discovery has fundamentally challenged our traditional understanding of atmospheric electricity and radiation exposure at high altitudes, creating an entirely new frontier in meteorological research that bridges multiple scientific disciplines. What makes dark lightning so extraordinary is the complex physics behind it. While conventional lightning results from the separation and neutralization of positive and negative charges within thunderclouds, dark lightning emerges from a far more complex set of interactions. When powerful electric fields develop within storm systems, they can accelerate electrons to nearly the speed of light. These high-energy electrons then collide with air molecules, producing gamma rays through a process called Bremsstrahlung radiation. Perhaps most fascinating is dark lightning's production of antimatter. When the gamma rays interact with atomic nuclei in the atmosphere, they generate electron-positron pairs, with the positrons being the antimatter counterparts to electrons. This natural production of matter-antimatter in our atmosphere was once thought impossible outside specialized physics laboratories or cosmic events. The entire process unfolds in less than a millisecond, releasing energy equivalent to that of a small nuclear explosion, yet confined to a relatively narrow column of air extending upward from the thundercloud into the upper atmosphere. Meteorologists have discovered that dark lightning doesn't occur in isolation but appears to complement conventional lightning. Research from Florida Tech University indicates that dark lightning often precedes or follows visible lightning strikes, suggesting a complex interplay between these forms of atmospheric energy discharge. The electromagnetic signature of dark lightning differs significantly from regular lightning, operating at frequencies millions of times higher than those produced by conventional lightning bolts. This relationship helps scientists understand the complete energy discharge cycle within thunderstorms, revealing that what we've observed visually for centuries is only part of a more complex atmospheric electrical system. The timing between dark and conventional lightning events provides crucial clues about the electrical dynamics within storm clouds and may eventually help improve prediction models for severe weather events. Commercial aircraft routinely divert around visible thunderstorms, but dark lightning presents a unique challenge because pilots cannot detect it. When aircraft fly through or near thunderclouds at altitudes between 10,000 and 40,000 feet, they may inadvertently intersect with these gamma-ray emissions. A 2023 study published in the Journal of Geophysical Research, Atmospheres estimates that approximately one flight per month worldwide may encounter a significant dark lightning event. The radiation dose potentially delivered during such encounters is concerning. A single dark lightning event can expose passengers to radiation equivalent to 10 chest X-rays in less than a millisecond. While this remains below dangerous thresholds for single exposures, the aviation industry and regulatory bodies are only beginning to assess the long-term implications for frequent flyers and flight crews who might experience multiple exposures throughout their careers. The radiation risk presents a challenge because current flight protocols focus primarily on turbulence and icing hazards when navigating thunderstorms. Pilots maintain specific distance requirements from visible storm cells, but these guidelines were developed without consideration for the invisible radiation hazards that may extend beyond the visible cloud boundaries. Aviation medicine specialists are now considering whether cumulative exposure to dark lightning events could contribute to the already elevated radiation exposure experienced by commercial aircrews. Flight crews who regularly fly at high altitudes are already exposed to higher levels of cosmic radiation that is less filtered by the atmosphere. The addition of potential dark lightning exposures adds another layer of concern for occupational health in the aviation industry. While a single exposure from dark lightning falls below dangerous acute thresholds, the long-term effects of multiple exposures throughout a career remain unknown. This uncertainty has prompted medical researchers to begin examining potential biological effects of the specific radiation profile produced by dark lightning, which differs from other radiation sources in both intensity and duration. The rapid, intense burst of gamma radiation presents a unique exposure scenario that doesn't neatly fit into existing radiation protection frameworks. Monitoring dark lightning presents significant technical challenges. Unlike conventional lightning detection networks that track radio frequency emissions, dark lightning requires specialized gamma ray detectors. Currently, NASA's Fermi Gamma Ray Space Telescope and the European Space Agency's ARSIM, Atmosphere-Space Interactions Monitor, installed on the International Space Station in 2018 are the primary tools for studying these events from orbit. In a breakthrough announced in March 2023, scientists at the Florida Institute of Technology developed the first ground-based detection system capable of identifying dark lightning events in real time. This network, expanding across the southeastern United States, uses specialized scintillation detectors to distinguish the unique gamma-ray signature of dark lightning from background radiation. The detection technology draws upon advances originally developed for particle physics research. The detectors use sodium iodide crystals that emit tiny flashes of light when struck by gamma rays. These flashes are then amplified and analyzed for their energy signature and timing patterns, allowing researchers to distinguish dark lightning from other natural radiation sources. This cross-disciplinary approach demonstrates how fundamental physics research often yields unexpected applications for environmental monitoring and public safety. The Federal Aviation Administration recently acknowledged dark lightning as an emerging concern, allocating $4.3 million in research funding in late 2022 to better understand the phenomenon. This recognition marks a significant shift in how aviation authorities approach thunderstorm-related hazards. The International Commission on Radiological Protection is currently reviewing whether to include dark lightning exposure in its recommendations for occupational radiation limits for aircrew members. These regulatory developments signal growing awareness of dark lightning's potential impact on aviation safety protocols. The funding will support expanded detection networks, improved modeling of how dark lightning forms within storms, and better assessment of radiation exposure risks at various flight altitudes. This coordinated research effort brings together atmospheric scientists, radiation biologists, and aviation safety experts in an unprecedented collaboration to address this newly recognized hazard. Beyond aviation concerns, atmospheric scientists are exploring the potential ecological impacts of these radiation bursts. Preliminary research suggests that dark lightning may contribute to upper atmospheric chemical reactions, potentially affecting ozone concentrations in ways not previously accounted for in climate models. The high-energy particles produced during dark lightning events can trigger chemical reactions that alter the composition of the upper atmosphere, particularly affecting nitrogen compounds that play important roles in atmospheric chemistry. A comprehensive international research initiative launched in April 2023 aims to combine satellite observations, aircraft measurements, and computer modeling to create the first global dark lightning risk assessment by 2025. This initiative will map the global distribution of dark lightning events and examine their potential cumulative effects on atmospheric chemistry, especially in regions with frequent thunderstorm activity. Understanding these effects may require updates to climate and atmospheric models that currently don't account for the chemical changes triggered by these high-energy events. The scientific community is also investigating potential benefits from studying dark lightning. The phenomenon provides a natural laboratory for examining high-energy particle physics that would otherwise require massive accelerator facilities. Astrophysicists have noted similarities between dark lightning processes and certain events observed in distant galaxies, suggesting that our atmosphere might be an accessible model for understanding cosmic radiation phenomena. Additionally, the antimatter produced during dark lightning events could potentially inform future energy research, as antimatter represents the most energy-dense fuel theoretically possible. By studying how nature efficiently produces antimatter in these events, scientists may gain insights applicable to controlled antimatter production for research or future advanced propulsion systems. The unique conditions created during dark lightning events allow scientists to observe particle interactions that would be difficult or impossible to recreate in laboratory settings, making Earth's atmosphere an unexpected but valuable resource for fundamental physics research. As our understanding of dark lightning grows, it represents a fascinating intersection of atmospheric physics, aviation safety, and radiation biology that may reshape protocols for storm avoidance and high-altitude flight planning in the coming years. The discovery and ongoing research into dark lightning highlight the importance of cross-disciplinary scientific collaboration, with meteorologists, physicists, aviation specialists, and medical researchers all contributing crucial perspectives. As detection networks expand and more data becomes available, we can expect significant advances in predicting and monitoring these events. The development of real-time dark lightning forecasting could eventually be integrated into aviation weather services, providing pilots with another tool for safe navigation through stormy skies. International coordination is essential, as dark lightning occurs globally but with regional variations in frequency and intensity. Sharing data across borders and between scientific disciplines has accelerated understanding of this phenomenon and will be crucial for developing effective monitoring and safety protocols. What began as an obscure atmospheric curiosity detected by chance in the 1990s has evolved into a serious scientific discipline with implications for multiple fields. Dark lightning exemplifies how nature continues to surprise scientists with phenomena operating just beyond our perceptual reach. As detection technology improves, researchers expect to discover more about the formation conditions, frequency variations, and potential long-term effects of these events. Future research will likely focus on developing more sensitive and widespread detection networks, creating better predictive models for when and where dark lightning might occur, and establishing clearer guidelines for radiation protection in aviation. The next generation of satellites and ground-based detectors will provide unprecedented detail about the structure and behavior of dark lightning, potentially revealing variations or subtypes not yet identified. Climate scientists will incorporate these findings into atmospheric models, while aviation authorities will develop more nuanced storm avoidance protocols based on both visible and invisible hazards. This humbling reminder that our planet still harbors natural secrets continues to drive scientific curiosity and cross-disciplinary collaboration, ensuring that our understanding of Earth's complex systems continues to evolve. Dark lightning represents one of the most fascinating discoveries in atmospheric science in recent decades. This invisible phenomenon shoots antimatter and gamma radiation from thunderclouds into space, occurring approximately 1,000 times daily across our planet. Unlike the lightning we can see, dark lightning operates in silence and invisibility, detectable only through specialized instruments. The implications extend far beyond scientific curiosity, from radiation exposure concerns for aircraft passengers and crew to potential effects on atmospheric chemistry and climate models. As detection networks expand and international research collaborations intensify, we're witnessing the evolution of a new scientific field that bridges meteorology, physics, aviation safety, and medicine. The $4.3 million in FAA funding and the Comprehensive International Research Initiative launched in 2023 signal growing recognition of dark lightning's importance. This phenomenon reminds us that even in our age of advanced technology and comprehensive Earth monitoring, our planet still harbors extraordinary secrets just beyond our perception, natural processes that challenge our understanding and inspire continued scientific exploration. Dark lightning exemplifies why cross-disciplinary research remains vital, as we continue to uncover and understand the complex, invisible forces shaping our world. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.